All right, today we're going to dive into a topic of materials and material selection. The topic of materials is so important to our modern society that entire disciplines and fields of study, both within science and engineering, have evolved over the centuries around this one topic. Material engineers and chemists spend their entire careers exploring the composition and properties of these different materials. They use this knowledge that they gain throughout explorations to fashion new materials that can meet the requirements of different designs. As a result, a designer engineer has a wide variety of materials to choose from. Within this unit, we focus on the 5 types of materials that are commonly used in engineering applications, and those include metals, organic materials, ceramics, polymers, and composites. Each type of material has a special quality and property. It has proven applications as well as limitations, advantages and disadvantages over other material uses. As such, a designer engineer must have a broad understanding of these various materials so that they can make intelligent decisions regarding the physical makeup of an engineering solution. So, what exactly are materials? Materials are simply tangible substances that make up physical objects. Since there's so many different materials that are available to us, we wanted to be able to house and categorize all of them. So to do this, if you want to visit mattweb.com and spend a few minutes looking at their website, what it is basically a searchable database that lists over 76,000 individual and unique materials along with their properties. Let's take a look at the history of materials. Materials such as metals have been so important to the development of human civilization and technology that 2 of the prehistoric periods of human history, both the Bronze Age and the Iron Age, are characterized by the type of metal that was most advanced during these time periods. Can you think of another time in America when material availability played such a critical role in defining a culture? What first came to mind for me was the Industrial Revolution. By developing the use of iron and steel, we were able to transform economies that had been based on agriculture into economies based on large-scale industry, machining and manufacturing, and the factory system. New machines, new power sources, and new ways of organizing work made existing industries not only more productive, but more efficient. So as you can see, materials continue to change our world, whether through commercial sources for application in engineering design, or for those that are extensively used in high-profile engineering applications. Advancements in both materials, technology, and science create continued advancement possibilities for each sector for many more years to come. Let's go ahead and look at the composition of materials. Any material that is composed of only one type of atom is called an element. Any material that's composed of more than one type of atom is called a compound. Many elements differ dramatically in their chemical and physical properties, but some elements are similar in their behaviors. To help organize these materials, we've divided them into 3 categories: metals, nonmetals, and metalloids, based off physical properties including the element's boiling point, melting point, density, color, hardness, and texture, as well as their chemical properties including their reactivity to acid, oxygen, and flammability. As we discussed before, every element has unique atomic structure. Scientists know of roughly 109 basic elements at this time, although this number has a habit of changing. All matter is composed of combinations of one or more of these elements. 91 of them naturally occur on or in the earth, while the others are man-made. To help categorize these basic elements and some of their physical properties, we've organized them using the periodic table. They're based on individual properties and are grouped according to their shared properties. You may recognize the names of some of these basic elements, including hydrogen, helium, oxygen, iron, copper, gold, and aluminum. As you can see by the shades of colors on this periodic table, that these groups represent the elements that contain shared properties. For instance, metals are shaded in yellow, nonmetals are shaded in green, and metalloids are shaded in purple. Now let's look at some distinguishing characteristics between these 3 categories of elements, starting with metals. Most elements can be considered metals. They are grouped together in the middle to the left-hand side of the periodic table. When it comes to metals, some distinguishing characteristics include that they're mostly solid at room temperature, they're shiny, they have a high melting point, They're good conductors of heat and electricity because they typically have 1 to 3 valence electrons. They're malleable, which means they have the ability to deform under compression. They're ductile, which means they have the ability to deform under tension. And they typically can reflect light. Now let's turn our attention to nonmetal elements. The nonmetal elements occupy the upper right-hand corner of the periodic table. Nonmetal elements include the nonmetal group, halogens, and the noble gases. These elements have similar chemical properties that differ from the elements considered metals. The nonmetal element is simply a subset of these elements. Hydrogen acts as a nonmetal at normal temperatures and pressure and are generally accepted to be part of the nonmetal group. Properties of nonmetals include that they're dull, not shiny, poor conductors of heat and electricity, they're not malleable or ductile, and are usually brittle. And for our third category of classifying elements, we have metalloids. As we've seen, metals and nonmetals have very different properties. However, metalloids have some properties from each of those two groups. Where metals are used to build structures for jewelry and coins and for electrical wiring, nonmetals are often essential for life as they often are used in medicines, fertilizers, and disinfectants. But metalloids are used as semiconductors that allow agents to moderate the properties of metals. Metalloids follow a zigzag or stepladder between metals and nonmetals on the periodic table. The identification of elements as metalloids is a judgment call. For example, some exclude boron from this group while others consider carbon to be a metalloid. As I previously stated, materials are composed of 2 or more elements known as compounds. Since a compound chemically combines these elements together, their properties are going to be different from the elements from which the compound was originally created. Compounds and mixtures may also be identified as metals, metalloids, or even nonmetals. With compounds, their element combination are not random. Rather, they're based on specific mass ratios. An example would be water. H2O is equivalent to 1 gram of hydrogen to 8 grams of oxygen. It's important to note that compounds can only be broken down through chemical processes. They cannot be physically separated. When it comes to mixtures, a mixture is made by simply mixing together 2 or more substances. As a result, no new chemical bonds are formed. They do not have any definitive ratios, and they can be physically separated. So with all that said, based on a material's composition and its distinguishable properties, we've gone ahead and created 5 material classification categories that are commonly used in engineering applications. These 5 include metals, organic materials, ceramics, polymers, and composites. When it comes to metallic materials, metals are divided into 2 categories, ferrous and non-ferrous metals. Ferrous metals are those that contain iron. A major drawback of most ferrous metals is corrosion. You see, iron bonds easily with oxygen, which is readily available in both water and air. This causes ferrous materials such as steel to rust when they're exposed to outside environments. To combat this, elements such as nickel and chromium are alloyed with the steel to produce corrosion-resistant metals called stainless steel. If you have a metal kitchen sink, it is most likely made of stainless steel. Iron is a very important element in the fields of mechanical and civil engineering because most machines, bridges, and buildings are comprised of objects that contain iron in them. Non-ferrous metals are simply those that do not contain iron. Examples include gold, silver, and copper. Of all the non-ferrous metals, gold is possibly the most well-known because it's a precious metal. A precious metal is one that is relatively scarce, highly corrosion resistant, and it's valued for its color, luster, and malleability. Gold is one of the best conductors of electricity, which is why it can be found as a coating on electrical contacts of circuit boards and other electronic components. Ceramics were the first human-made materials. The earliest archaeological evidence of fire-clad objects date back all the way to 24,000 BC and were found in an area that is now part of the Czech Republic. Ceramic materials are compounds consisting of metal and nonmetal elements. They are used as thermal and electrical insulators, and their mechanical properties include high strength at high temperatures and brittleness. Clay is one type of ceramic material. Other ceramic materials, both natural and synthetic, are employed in engineering applications. In fact, there are several categories in which ceramic materials fall. These include whiteware, structural clay, refractories, glass, abrasives, and cement and concrete. The breakfast or dinner that you eat at home was most likely served on a ceramic plate that falls under the category of whiteware. Porcelain is a revered example of ceramic that also falls under this category. The ceramic materials contained in bricks must withstand large compression loads. Bricks are one of the most common and oldest examples of structural clay. Clay bricks are believed to have been developed all the way back in 3000 BC, and other examples of structural clay objects today include floor tiles, chimney flues, and drain tiles. The word refractory literally means to resist heat. Refractories are non-metallic ceramic materials that are applied in situations where extreme temperatures, mostly above 1,000 degrees Fahrenheit, are encountered. Such materials are used in crucibles, incinerators, nuclear reactors, and engines. Perhaps the most widely publicized application of refractory ceramics is in the Space Shuttle's thermal protection system. 34,000 individually shaped tiles that make up the Space Shuttle's outer skin. These tiles prevent the shuttle from burning up because of the extreme temperatures that are generated when entering Earth's atmosphere. As with most ceramic materials, refractories have one major weakness: they're brittle. The disadvantages was a cause for the Space Shuttle Columbia disaster that occurred in February of 2003. The shuttle suffered damage to its ceramic heat shield during liftoff when a piece of foam insulation struck the leading edge of the shuttle's left wing. The damaged area of the wing caused catastrophic failure upon re-entry into Earth's atmosphere 2 weeks later. The importance of refractory ceramics cannot be overstated because it was the development of this material around the 16th century that led to the Industrial Revolution. Glass is a ceramic material that's made from mostly sand. It was first discovered in Egypt around 8000 BC as an unexpected glaze that would appear on pottery that was fired in an overheated kiln. The glass we're familiar with today, however, was not generated until about 15,000 BC. Common engineering applications of glass include windows in buildings and cars, lenses in eyewear, microscopes, and telescopes. Other not so well-known engineering applications of glass include fiber optic communication lines, insulation in homes, and reinforcement fiber and composite materials. When it comes to abrasives, if you've ever used a piece of sandpaper or sharpened a knife using a grinding stone, then you've used a ceramic material that falls under this category of abrasives. Diamonds, both natural and artificial, are considered ceramic materials that are used as high-quality abrasives in drilling and grinding tools. Another engineering application of abrasives include ceramic cool-tutting inserts that are often used in place of traditional high-speed steel tools and high production volume machining applications. Cement, which is also known as mortar, is a dry powdery substance that serves as a binder when mixed with water. It is most commonly recognized as the glue that holds bricks or block walls together. Cement is also an important component of concrete. Concrete is a mixture of cement, sand, stone, and water that can be molded into virtually any shape. Unlike clay, neither cement nor concrete are fired. Rather, they require time to cure in oxygen-rich environments. In fact, a concrete foundation wall must cure for 28 days before a building can be constructed on top of it. By weight, concrete is the most extensively used of all human-made materials, and it's commonly applied to bridge, dam, and tunnel construction where enormous compressive loads must be carried. With organic materials, they're defined in modern chemistry as a carbon-based compound, originally derived from living organisms that now include lab-synthesized versions as well. They are renewable and sustainable materials. Examples of various organic materials include paper products, cardboard boxes, magazines and books, compost waste piles, yard trimmings, leaf piles, and food scraps. The words polymer and plastic are often used interchangeably, but they're not synonymous. The word polymer is an umbrella term that encompasses all high molecular weight organic compounds, either naturally occurring or synthetic, that are comprised of at least 100 repeating chains of simple molecules. Polymers are divided into two groups: plastics and elastomers. An elastomer is a natural or synthetic polymer having elastic properties. An example would be rubber. Many people consider plastics to be new materials. Although it's true that most synthetic or human made plastics are used today and have been around for less than 100 years, natural plastics have been used for decorative purposes for over hundreds of years. Natural plastic materials are moldable when heated and remain in their desired shapes when cooled. Virtually all commercial plastic products that we purchase at the stores are examples of synthetic polymers. This means that they were formed as a result of human controlled chemical processes. Some plastics can be reshaped over and over again, while others remain in their initial form and cannot be remolded. It is this quality that defines the two categories into which all plastics are divided: thermoplastics and thermosetting plastics. If a plastic can be reheated and reformed, then it belongs to the category known as thermoplastic. Thermoplastics you're probably familiar with include nylon, polyester, and Teflon. A thermoplastic is a plastic that's comprised of disconnected polymer chains that are capable of slipping past each other when heated and return to a rigid state when cooling. An easy way to remember thermoplastics is to use the analogy of a bowl of cold but cooked spaghetti. Each strand of spaghetti represents a polymer chain that is finite in length and is not connected to any other strand. When reheated, the mass of spaghetti becomes pliable and can be reshaped into many different forms. The ability to be reheated and reshaped makes thermoplastics well suited for recycling. Significant effort has been made in the plastics industry to make the process of recycling easier for the consumer by incorporating standardized recycling symbols into its plastic product. As I mentioned earlier, thermosetting plastics are plastics that become set in their solid state once they're molded. Consequently, they cannot be remolded, which severely limits their ability to be recycled. Though this may be viewed as a disadvantage, thermosetting plastics do have an edge over thermoplastics in the fact that they can withstand higher temperatures, they're harder and stronger, and are far less susceptible to chemical decomposition from acids and solvents. Some of the more popular thermosetting plastics include epoxy, polyester resin, and polyurethane. A thermosetting plastic starts out as two different substances called resin and a hardener, which are combined together in proper portions to generate a chemical reaction. A resin is a gum-like solid that contains polymer molecules that cross-link when combined with a hardener. The hardener is a catalyst that causes the polymer molecules in the resin to become cross-linked to each other. This process is called curing. When the curing process is finished, the material will remain in a fixed solid state. The cross-linking of polymers is what chemically separates a thermosetting plastic from a thermoplastic. Returning to the analogy of a bowl of spaghetti, imagine that each strand of spaghetti is tied together to form one giant piece of spaghetti. In theory, a thermosetting plastic is one giant polymer molecule. As such, the molecular weight of the molecule is so high that the temperature at which the material would melt is beyond its own thermal degradation temperature. This means that a thermosetting material will burn and char before it reaches its melting point. The most popular application of polyester resins is a combination with either polyurethane foam or reinforcement such as fiberglass, Kevlar, and carbon fiber. The result is a composite material that's used to make boats, automobile and aircraft body panels, golf carts, tub and shower units, helicopters, and even the blades of wind turbines. The exterior applications take advantage of the material's good resistance to water and weather conditions. Polyurethane is one of the most versatile and widely used thermosetting plastics. It is produced in many forms such as protective coatings, elastomers, rigid plastics, adhesives, foams, and fibers. It is also used as a water-resistant adhesive for gluing wood items and other items of similar material. Foam polyurethane is also available in many different densities. The most flexible foams are used in furniture cushions, mattresses, and car seats. Low-density rigid foams are employed as thermal insulators in refrigerators, freezers, and even buildings such as spray foam insulation. As we saw on the previous slide, all plastics are polymers, but not all polymers are plastic. For example, a rubber band is made of a polymer material that falls under the category of elastomers. Elastomers are natural or synthetic polymers that have the ability at room temperature to stretch to at least twice their length and return back to their original size after unloading. Some elastomers can be reshaped or reheated, whereas others become set once they have been molded into shape. Elastomer materials are used in flexible adhesives, components such as tires that absorb shock, protective gloves, waterproof jacketing, power transmission belts, and even adjustable tension straps. One process commonly used with rubber materials is vulcanization. This is a chemical process that's used to form strong bonds between adjacent polymers to produce a tough, strong, hard rubber. This vulcanization process is commonly used in automobile tires. This way, the vulcanized rubber used in tires won't crack or stiffen in cold temperatures, giving it exceptional resiliency for hard use. The subject of composites has been saved for last because they represent blends of all other categories of materials. A composite material is a solid that is comprised of two or more distinctly different materials that are intentionally combined in layers or mixtures to exploit and enhance certain material properties. Take, for example, plywood. Plywood is a composite material that's formed by thin sheets of wood that are glued together using high-strength thermosetting plastic adhesives. The result is a material that has a greater strength-to-weight ratio than a board of equal geometry made from a single species of wood. Composite materials are not without their disadvantages, though. Generally speaking, they incur higher material costs, are harder to manufacture than traditional materials, and they tend to utilize materials that are non-recyclable and are therefore environmentally problematic. So examples of various composites include layer composites, which alternate layers of materials that are bonded together. So examples would include, again, plywood, safety glass, and formica. We also have particulate composites, which are discrete particles of one material being surrounded by a matrix of another material. Some examples of these types of composites would be concrete, asphalt, powdered metals, and ceramics. And then we also have fiber reinforced composites, which are composed of continuous or discontinuous fibers embedded in a matrix of another material. Examples include Kevlar, steel reinforced tires, fiberglass, and graphite epoxy. So we've talked about different materials and how we classify and categorize materials. Now let's talk about material selection. When it comes to material selection, the basic question is, how do we go from selecting a material for a given part? This may seem like a very complicated process until we realize that we're often restrained by choices we've already made. For example, if different parts have to interact, then material choice then becomes a little bit more limited. When we talk about choosing materials for a component, we have to take into account many different factors. These factors include material properties, product function, the expected level of performance from a material, the material's cost and availability, environmental conditions, and how the material will degrade naturally over time or when exposed to various substances. In order to determine which material selection is best to use, we consider their known mechanical, thermal, electromagnetic, and chemical properties. When it comes to selecting materials based off their mechanical properties, we consider the material's strength, hardness, ductility, and stiffness. As mechanical engineers, we mostly deal with metals. Metal properties tend to be well understood, and metals are somewhat forgiving materials. We can make small mistakes, or even sometimes bigger ones, and get away with a poor design as a result of the metal's forgiving nature. We see ceramics and composites all around us, but they tend to be used in specialized applications because of their fabrication costs. This, however, is changing. Plastics are among the most common modern material choices in today's society. In large volume production, plastics are very inexpensive. However, in small productions, plastics can be an extremely expensive choice due to their high tooling costs. When it comes to selecting a material based off its thermal properties, we consider how the material is affected by changes in heat and temperature. Specifically, we consider its thermal capacity, which is the heat storage capacity of that material, the thermal conductivity of the material, which is the capacity for that material to transport heat, and the thermal expansion of that material, or in other words, how a material expands or contracts if the temperature is raised or lowered. When it comes to electrical properties, we're looking at how a material responds to electromagnetic fields. Considering electrical conductivity, is the material an insulator, a semiconductor, or a conductor, or even a superconductor? And is the material thermoelectric, which means is there electrical stimulus provoked by thermal responses? And finally, when it comes to selecting materials, we have to take into account its chemical properties. Specifically, we want to know how that material is going to be responding and impacted by different environments. For instance, we want to know if that material is exposed to oxygen-rich environments, is it going to corrode over time? We also want to know if we use that material with another material, is it going to have some type of damaging effect on the other materials being used in the process? And finally, we also want to consider, is that material have the ability to ignite or even combust when certain applications are applied to it?